Test 1, 2, 3. Allô? Ah!
Il y a un modérateur pour ça fait un reminder, mais on sent une qualité dans. C'est bon, ça marche. Les trucs à la vidéo là.
Ouais.
Si je viens de cliquer sur le lien de l'annonce.
Ouais.
Ça, c'est. Ouais. J'espère que les gens ils font ça. Le message est envoyé.
Test. Pardon?
Why you are disconnected from the Skype?
Ah, c'était juste pour régler des trucs. Sans que ça soit. Bonjour Sébastien.
Oui, bonjour Gaëtan.
Est-ce que vous m'entendez?
Oui, oui, c'est bien, j'entends bien.
Bonjour Sébastien.
Bonjour Florent.
Le jury est au complet ici.
Normalement, je l'ai mis sur les haut-parleurs.
D'accord, bien commencé.
Avec ce haut-parleur-là, ça peut fonctionner comme on va avoir de l'écho.
Ouais.
Hello.
Comment vas-tu tout le temps?
Ça va?
Tu restes un peu après ou pas?
Oui, un peu.
Il ne faut pas que les deux micros soient. Il y a un micro aussi. Celui-là, peut-être. Sinon, pour les questions, peut-être on peut faire le switch. Voilà. Pour ta présentation, celui-là. J'ai pris un taxi à Christian pour 5 heures. Ça sera bon pour 3 heures. Ouais, c'est jouable.
Ah, donc il faut que j'éteigne ce haut-parleur-là.
En fait, j'aimerais bien que tu fasses.
Je vais éteindre mon haut-parleur ici. Par contre, je vais laisser mon micro allumé. Bonjour, Sébastien,
Ouais, bonjour Pierre, je vous entends, hein, c'est bon.
vous m'entendez?
Ouais. C'est bon. Oui,
On n'entend pas encore.
ok. Donc moi, je suis en train de parler là.
Il y
Et
a
vous m'entendez pas.
ce micro-là et laisser le micro de Gaétan.
Sinon, on essaie ça quelqu'un. Vas-y, essayons. Donc, attends, je vais vous demander. Je vais réessayer. Bonjour Sébastien, est-ce que vous m'entendez?
Oui, bonjour. Bonjour Pierre, je t'entends.
Bonjour. Très bien, on vous entend, c'est parfait.
Super.
Voilà.
Normalement, là. Ah oui, là, du coup. Oui.
Hello Christian.
Hi, who's that? Ah, here we go. Good to see you.
Yeah, indeed. Sorry for not being with you.
Physically, could you? Okay.
Je peux le mettre à Sébastien en Good afternoon, everyone. My name is Pierre Alliez. I'm a senior researcher at Yuliya here. I will be the president for this PhD committee of Gaétan BAHL on deep learning architecture for onboard satellite for image analysis. Let me first introduce the committee members, and I will start by Professor Heipke, who is professor in photogrammetry and remote sensing at Lefèvre University in Hanover, in Germany.
Thanks very much for the invitation. That's it.
Thank you. Then Professor Sébastien Lefèvre, who is in a video conference, as you see on the screen, professor in computer science at the University of Bretagne Sud and also at Adrien in Van.
Thank you.
Those are the two thesis reviewers. Then there are three examiners. The first one is Adrien Girard from IRT Saint-Exupéry, who is a project manager. Yuliya Tarabalka, research director from Lutkarta, and myself. Okay, and to finish the committee, the thesis advisor is Florent Lafarge, who is a senior researcher at Adrien. Okay, we have everyone with us. Everything is ready. Then Gaétan BAHL will give you 45 minutes approximately for your defense.
Thank you, Pierre. So, can you cut your mic?
Yes.
And speakers?
Can you hear me? Okay. Hello, everyone. Thank you all for being here. I was not expecting so many people. Welcome to my PhD defense entitled Deep Learning Architectures for Onboard Satellite Image Analysis. This project was prepared at INRIA in the Titan team under the supervision of Florent Lafarge, and it was funded by the CR project at IRT Saint-Exupéry. First, a little introduction. Today, Earth observation generates large amounts of data. This is because we have more than 900 Earth observation satellites currently in orbit. And these satellites produce hundreds of terabytes of data every day. Nowadays, we are seeing the development of constellations of satellites that have really short revisit times. So we can get a picture of the same place even multiple times a day. Also, we have seen the development of multispectral sensors or even hyperspectral sensors, which creates even more data. The resolution of these sensors has increased as well, and we can even reach sub-meter resolutions. So what do we do with all of this data? How do we deal with it? Well, the thing is, we don't actually need all of it, or probably not. For example, on this image, high-resolution image of a ship, we see that there is only one ship, and the number of ship is just a single number, or the position of the ship can be expressed using 4 integers. So we can reduce the amount of information by only keeping the interesting information. On this cloud-covered image, it's the same thing. We can express the cloud coverage using a single number. Or we could decide that there are simply too many clouds here and get rid of the image entirely. On this image of a forest fire, what's important is that there is a fire. So we can send an alert saying that there is a fire, and this is only a single number. Or we could estimate the quantity of forest that has burnt, and again, this is a single number. So what would be interesting is to extract all of this information directly on board. This would allow us to reduce the bandwidth usage between the satellites and the ground, reduce the storage usage, both aboard on the satellites and on the ground. It would reduce the latency between the acquisition of an image and the decisions that come after that. And also it would reduce the human labor. Also, it would maybe allow us to get real-time alerts directly from satellites. There are many computer vision tasks that we could want to perform directly on board, such as classification or object detection. And these tasks nowadays are usually performed using deep convolutional neural networks. These networks have lots of parameters, from millions to billions of parameters. They have really high hardware requirements. They require GPUs, so graphics card inside really powerful computers. And they have a high memory usage, a high power consumption, and a high processing time. So these methods are impractical to use on board satellites, which is why we need to develop low power solutions based on these networks. There are some constraints that we need to work with. So storage space and memory are really limited. We have a low compute power. The satellites are not upgradable. Once they are launched, we cannot upgrade them. The transmission number is limited because the satellite needs to be above a ground station in order to transmit the data. The bandwidth is limited. The processing time is limited. And this means that we need to design lightweight, low power neural networks that also have compact outputs that we can store on board until they can be transmitted. So during this thesis, we focused on three major problems. The first one being pixel level semantic segmentation. The second one is the regression of compact object contours, which is similar to instant segmentation, and the extraction of compact road graphs. So let's start with semantic segmentation. So some techniques have already been developed to reduce the size of neural networks, such as pruning or weight quantization. In this project, we choose to focus on the OPSAT satellite, which was launched by the European Space Agency, in 2019. And this satellite features a really small FPGA. So these techniques are not enough reduction, do not provide enough reduction to fit our needs. Some people have already tried to create some low power semantic segmentation architectures, but they still have too many parameters and they require too much RAM because of the use of skip connections inside the architectures. Our approach is based on two very popular neural networks. The first one is UNet. So we develop a compact UNet where we remove the skip connections because we find that they are not particularly useful for our use case. We use depth-wise separable convolutions in order to reduce the number of parameters and the compute burden. We also remove some convolution stages. So you can see that there are 6 convolution stages or steps in the UNet, in the original UNet, and we only keep 3. And each convolution has a low number of filters. This allows us to go down from 30 million parameters to around 50,000 parameters. We also design an even more low power architecture, which has 10,000 parameters. Our second network is based on FCN, and it uses a lightweight encoder, also depth-wise separable convolutions, a low number of filters as well. And our smallest version uses atrous convolution, which widen the field of view of the network. For the decoder, we use a simple bilinear upscaling. And these networks have around 1,000 parameters or 300 parameters. So this is really low. For the experiments, we choose to focus on cloud segmentation. And this is an interesting problem because more than 50% of the planet is covered by clouds at any time. And it would be really interesting to perform onboard cloud segmentation to estimate the cloud coverage and eliminate cloud pixels or images that contain too much clouds. And there are some challenges on the OPSAT satellite because it only has an RGB sensor. And differentiating between clouds and snow is hard to do with RGB because the clouds have the same radiometric properties as snow. We use two datasets, the 38 cloud dataset, which has a 30-meter resolution, and the Cloud Peru 2 dataset with a 3-meter resolution. We only keep the RGB bands in these datasets. Sorry. Here we plot the accuracy versus the number of parameters of our networks and competing networks. And what we aim to offer is a good compromise between accuracy and number of parameters at different levels of performance. So as you can see here, our CUNet achieves the same accuracy or even better as the original UNet with 1,000 times less parameters. And even our 300 parameters CFCN++ achieves respectable results. For qualitative results, we observe that even though the results of our networks are quite smooth, it's not a problem to estimate the cloud coverage. In particular, we see that on the third image, which is covered by snow, even the smallest network can differentiate between snow and clouds. We also run some forest segmentation experiments, and this is useful as well for the deforestation monitoring, for example. And we use the Slovenia 2017 dataset. In this task, we find that our networks also achieve good performance. The team at CR, the CR team at IRT, sorry, used one of our networks and converted it to VHDL and run an experiment on the FPGA of OPSAT directly in orbit. We used images captured by OPSAT in flight and fine-tuned our network. And this is an example of inference that was done directly on board last year. So to sum up this part, we have designed 4 low-power semantic segmentation architectures. They can be used for cloud and forest segmentation directly on board. And we have shown that RGB is enough to find the clouds in images using really small networks. Also, this was the first work on onboard cloud segmentation on an FPGA directly in orbit. The limitations of this work is that we used some handcrafted architectures, and we don't really know if they are applicable to more complex classes, such as buildings. Now, let's keep talking about semantic segmentation, but let's do it with another type of network, which is recurrent convolutional networks. Most Earth observation satellites are actually push broom satellites. This means that they have a linear array sensor, which captures images line by line as the satellite flies. This can create large images if we let the acquisition run for a long time. If we were to use a classical CNN inference on these satellites, it would have a high latency because we would have to wait until the whole image is acquired. It would incur a high memory usage and use a lot of storage space on board. So it would be interesting if we could find an architecture to process the image line by line as it is acquired. For this, we are going to use recurrent neural networks And these networks, RNNs, are networks with loops, and they have an internal state that allows them to keep the important information in memory. They apply a fixed set of weights at each iteration. And on the bottom right, you can see the LSTM, which is an example of RNN. Convolutional LSTMs have been used recently for processing of video frame by frame or for weather nowcasting. And in these networks, the linear operations are replaced with 2D convolutions. These networks have interesting properties. They have a really low memory usage. They can capture long-range dependencies and achieve a really low latency because the output is created at the same time as the input is ingested. So this is really interesting for our use case. We designed a small architecture called ScannerNet, and we used 1D convolutions instead of 2D because we want to process line by line. We only have 2 layers, no pooling, no peeping in the LSTM. And on the right, you can see the LSTM equations where we have replaced the linear operations with 1D convolutions. And the interesting thing here is that all of these operations can be implemented really efficiently using a single convolution operation. We can concatenate the weights of these convolutions and we get the concatenated output. We can just split it and use it for I, F, O, and G. And this is our network. We run a cloud segmentation experiment in order to easily compare to our previous work. And we focus on the accuracy of the networks, the memory usage for inference, and the latency. We have 2 versions of the network, one bigger one and a smaller one. And what we see is that they match the performance of CFCN and CUNet that we saw in the previous part, even though they can only look at one line at a time. So the results are similar, and the qualitative results look even more refined with ScannerNet because there is no special downsampling in the network. We process everything at the input resolution. So does this mean that we only need one line to perform segmentation? Well, not really, not quite, because we also ran an experiment with a 1D convolutional baseline. This is the top line in the table. And we see that without the RNN part, it really doesn't perform as well. So the RNN part is essential to keep important information. Then we test the memory footprint of these networks, and we find that using only 100 kilobytes of RAM, we can perform semantic segmentation. And this is really not a lot of RAM. What we see on the graph here is that at each IOU level, our networks use way less memory than our previous work. So even though CFCN and CUNet were already very efficient, we can do better with ScannerNet. Then we look at the latency. We define the latency as the delay between the start of the inference and the output of the first pixel of the segmentation map. So this is one line for the ScannerNet and the whole image for CUNet and CFCN. We performed this experiment on a Jetson Nano, which is a small computer. And both on the CPU and the GPU of the Jetson Nano, we achieve a really low latency. So in the worst case, it can be 2 times as fast, 2 times faster than the other networks. And in the best case, it's there is 6 times less latency. So to sum up this contribution, we designed an architecture for semantic segmentation that is specifically tailored towards push-bump sensors and memory-constrained environments. It achieves a really low latency, and it's ideal for on-the-fly processing. And it's a proof that we can use 1D convolutions for semantic segmentation in 2D. Now, let's move on to smooth contour regression. So here, let's start with a little bit of context. So object detection is the task of finding bounding boxes for each object in an image. And this means finding 4 values for each object. And some lightweight architectures have already been developed for this kind of task. However, this representation is not ideal because, as you can see on this image, the IOU of the bounding box and the ship is actually really low. There is a lot of empty space in the bounding box, so it doesn't represent the ship accurately. There are solutions to this, such as instance segmentation. And this is the task of finding binary masks for each object. And these masks also have some drawbacks because they are resolution dependent and they rely on heavier architectures for regression. So what we need is something that is in between these two tasks. And it's actually, we think it's contour regression. And this is the task of finding only the shape of an object with a periodic function. This can be done using 2 ways. The first one is a polar representation. So here we represent the shape of the object using a single periodic function, a 2π periodic function. This is not ideal because it can only represent star-shaped domains. The other way to do this is to use the Cartesian representation. And here, the shape of the object is described using 2 functions, x and y. And this can be used to represent any shape. So this is what we are going to use. Let's mention some related work on this task. The first one that I want to mention is ESE-seg. And it's a work based on the YOLO v3 detection network. And they use Chebyshev coefficients for the function rho. And they are not the best for this kind of task, because as you can see on this image of a plane, on the right of the plane, there is a discontinuity in the shape. Also, to train this network, they need to generate ground truth labels, which is not an easy task. The second one is polar mask, and it's based on FCOS, which is another detection neural network. And here, what they do is a direct polar coordinate regression. So their network directly finds the values of the function rho. And it's not ideal either, because they also need to generate ground truth labels for each object. So to convert the polygons to a polar representation using a center that they find on each object. And the output representation is not smooth because they have to use a limited number of rays. The final work I want to mention is FourierNet, and it is also based on FCOS. And here they use Fourier coefficients for the function rho, but they also have a Cartesian version. And they use the inverse Fourier transform as a shape decoder, which means that they can train directly on ground truth polygons. However, their Cartesian version gets bad results. Our method is also based on FCOS. So this is a classical detection neural network with a backbone, a feature pyramid network, and a head that is applied at different resolutions with shared weights. And this is the head that we designed. It is loosely based on the FourierNet head. And here it has 3 branches, a class prediction, a centerness prediction, and a complex Fourier coefficients prediction. So we also use the inverse Fourier transform as a shape decoder. The loss function to train this network is here. The first part is the chamfer distance, which we use for the polygon regression. So this is similar to Fourier nets. We use the centerness loss from FCOS, which is the binary cross entropy. We use the focal loss for classification, which is from RetinaNet. And we add two important regularization terms. So the first one is on the shape perimeter, and the second one is on the Fourier coefficients. So why do we actually need this regularization? Well, the issue with the chamfer distance is that it is only based on the position of points. It doesn't take the order of points into account, which means that the network can circle the objects multiple times. And in Fourier net, they try to counter this with a warm-up using an L1 loss. And this is not ideal because it complexifies the training, and it tends to tie each output point to a specific output of the network. Our solution is more simple. We use a simple L2 perimeter penalty, which we apply to every regressed contour. And you can see that we only circle the object once. But you can also see that the output is still not perfect. This is because the neural network tries to use too many Fourier coefficients. And this tends to create small loops in the output. So this is an issue. And also, we would like to favor sparsity in the Fourier coefficients in order to perform compression on board, so that we can store many object contours aboard the satellite, for example. The solution we found for this is to apply an L1 coefficient penalty. And using this, we finally found that the outputs circle the objects once and are really smooth, without self-loops. We choose to experiment on the COCO 2017 instance segmentation dataset using 3 different backbones for different performance targets. For metrics, we use the MAP for accuracy, the FPS for speed, and for the compactness of the output, we use the number of coefficients of the representation. Here, on these images, you can see some outputs of our smallest network. And we see that the regressed contours properly follow the shapes of the objects, and they are really smooth. On this comparison against ESE-seg, you can clearly see that Fourier coefficients are superior to Chebyshev coefficients for this task. Against Fourier nets, we see that our network doesn't have all of this erratic behavior, and this is also due to the self loops that we solve with the L1 penalty. On this table, we see quantitative results using the biggest backbone, so ResNext 101. And what we find is that we have a better accuracy than Fourier net, but we also use fewer coefficients than polar mask. This means that our method achieves a good compromise overall. We also compare our method to other types of methods, so snake-based or mask-based methods. And we find that, of course, we are not as accurate as these methods, but we are fast and we generate a really compact output. Finally, we use Darknet 53 to compare against ESE-seg, and we get similar results. But since we use fewer coefficients, our method is a little bit faster. There are still some limitations to our method. We don't actively prevent the creation of self-loops. We only try to prevent them. So occasionally they can still appear. So especially between the legs of animals for some reason. And this can happen sometimes. However, it's not a huge problem because the shapes generated in this way can still be usable. We also performed some experiments on low power hardware. And we find that we obtained up to 115 FPS on the Jetson Javier NX, which is a lot on a small system like this. So to conclude this project, we have developed a fast method for regression of smooth contours. We have a really compact representation that allows to compress the shapes. This method is easy to train because we can use ground truth polygons, and it is usable on low power devices. Finally, let's move on to fast road graph extraction. So mapping is a task that is usually done on the ground by annotators. So they look at satellite images and click on the roads to create a road graph. This is a slow and expensive process. In the future, we might want to perform this task in real time directly on board. On the right, you can see an image of a flood in Australia last year. And you can see that some of the roads have disappeared underwater, but some other roads still remain. So by using a map updated in real time from a satellite, we could favor the evacuation of the people of this region. So doing this task in real time would help with natural disasters, but also it could be used for traffic monitoring or defense. We want to use road graphs because they are really compact representation compared to road masks, and they are directly usable in geographic information systems. The current methods for graph extraction, road graph extraction, rely on two principles. The first one is iterative exploration. So these types of methods construct the map point by point by exploring the image. So they have a starting location, they apply a convolutional neural network around the location and predict the next move, and then apply a CNN again and again. So these methods are really precise and have a really good connectivity, but they are very slow because of all of these CNN applications. Also, they can generate incomplete outputs. As you can see on this picture, the network was not able to cross the highway at the top of the image on the top left. So the neighborhood on the top left is not mapped. Also, these methods need starting position. So we need to tell them where to start. And it's not an easy task. It can be done manually, but we cannot directly interact with a satellite to tell it where to start the exploration. So it's not ideal. The other type of method is based on segmentation. So they use a method similar to UNet to find a road mask, and they convert that road mask to a graph. So this is really easy to implement because it's a classical method and it's easy to train. But it's also really slow because we need to generate a segmentation and then convert it to a graph. And when the mask that is used is of bad quality, we can get images like this with bad connectivity. Our method is completely different from both of these approaches. We want to perform a single shot end-to-end road graph extraction. And our idea is that a backbone neural network will generate low resolution features, and a subsequent fully convolutional head will detect points of interest. After that, a graph neural network will find links between these points of interest. So the points of interest can be intersections, turns, dead ends, and stuff like that. Our method has multiple advantages. It's really fast, it's easy to train, it generates a really compact output because we work at a low resolution. And also it's really, really fast. So let's construct this architecture together. We start from an image and we compute the low resolution features using a backbone such as a ResNet. After that, we have a junction prediction branch, which will compute a heat map of the junctions or turns, etc. A second branch will be tasked with offset prediction, and it will find a 2D vector field that contains the exact position of each point found by the junction prediction branch. So using both of these outputs, we can position the points of interest precisely on the input image. Then a third branch will find node features that will be tied to each point that we find. And these node features and nodes will be fed to a graph neural network that will predict the edges between the points. We train this network using 3 losses: the binary cross entropy for the junction prediction and the edge prediction, and the MSE loss for the offset prediction. And this is the whole architecture. We perform experiments on the road tracer dataset, which is composed of big images of 8,000 by 8,000 pixels. And we use a single GPU for training, and the training takes about 24 hours, which is really low by today's standards. We also perform performance benchmarks on a single GPU. We compare our method against 2 iterative methods and 2 segmentation-based methods. For metrics, we use the junction F1 score, the pixel F1 score, and the APLS. Here is an example of output of our network done on a whole image. And we see that it performs really well. It finds pretty much all of the roads. And we see on the bottom left that, well, it might seem that there are a lot of points, but actually, no. It's because of the ground truth of the data set that contains that many points. And as you will see in the next slides, our output doesn't have really many points. This is a comparison against road tracer and deep road mapper. And compared to these 2 methods, ours can generate a complete output on the whole city. And this is a really difficult image. This is a picture of Tokyo, and it's the most difficult image in the road tracer dataset. So compared to both of these methods, our output is more complete. In terms of quantitative results, we perform similarly to road tracer. We are not as precise as VecRoad, but our method shines in other ways. And it's because our method is really, really fast. For a single image, we only use 21 seconds. Whereas a method like VecRoad will take more than half an hour for a single image. So for the whole data set, the difference is even more pronounced. So we are hundreds of times faster than these types of methods. Now let's take a look at the capacity of the output. And as you can see, for this simple neighborhood, our network only needs 4 points to completely map the image, whereas VecRoad uses many more points. And this is really important because remember, we need to store these outputs on board and transmit them to the ground. And also having a compact output like this will speed up subsequent applications of other graph-based algorithms, such as shortest path search our method still has some limitations. It can sometimes miss long stretches of roads without any points of interest. And there are maybe some solutions to this. We could insert some virtual points of interest inside the ground truth, or we could use a multi-resolution approach with an FPN. So to sum up this contribution, we have developed a new kind of method for graph extraction. So it's different from any other method that was used before. It's really, really fast. It's easy to train because we can use ground truth graphs. So we can grab them from OpenStreetMap and use them like this. The output has a really low complexity. And this means it's really efficient for transmission and storage. Also, this method can be used for any image to graph task. So we could use it for building extraction, but also blood vessel extraction, for example. So to conclude this presentation, in my thesis, I have developed compact and fast neural networks that generate compact outputs. And both of these components are really important. I have worked on 3 big tasks, let's say, and our architectures can be used about satellites, but also some other kinds of edge devices. So smart cameras, cars, smartphones. I would like to offer some perspectives for the next few years of deep learning. I think handcrafting and tuning of architectures like we did in the first part will cease to exist because of the development of neural architecture search. Embedded devices will keep getting faster. So the phones, the satellites will keep getting faster, but also people keep developing more bigger and bigger neural network architectures. So we still need to develop lightweight algorithms. This is really important because in today's world, we need to focus on doing more with less. And this is important for sustainability, for the environment, etc. We also need to develop explainability. Explainability is really important because as we move towards implementing neural networks inside the actual objects that we target, people will want to know why a neural network took a certain decisions. Think about smart cars, for example. And we need to develop explainability. Otherwise, the general public will never trust our networks. And I don't think I would trust them as well. Finally, we need to solve new kinds of problems. We shouldn't focus on leaderboards. While climbing the leaderboards of ImageNet or whatever by a few percentage points every year is fun, I'd say. It's not really that meaningful. We need to solve new problems, do it more efficiently, and yeah, focus on new kinds of tasks. So this is it. Thank you for your attention. Thank you for listening. And I'm ready for your questions.
Thank you, Gaétan. Let me start by the round of questions by the committee members, starting by the reviewers and Professor Christian Heipke.
Okay, well, thanks very much for your very illustrative, very interesting, and very understandable presentation.
Thank you.
Apparently some feedback, but maybe we'll get that into. Now I've come here to ask questions, so that's what I'm going to do now. I was wondering, you were talking about this network, what is it called? Architecture search. Yes. Now, is there a theory of how you would simplify existing networks, as you did, for instance, in the first part of your work, so that we could not only do some try and error and see that while the network is less heavy, it still has the same similar quality in terms of the results. Is that something you could predict? If you do such and such things, then for such and such application, you expect these results? That would be great, wouldn't it? And does the network architecture search go in that direction?
I think it's going in that direction because we have seen some the development of some hypernetworks, and these hypernetworks, they learn to generate a neural network that has a number of weights, and I think it's going in that direction because even though there is not really a theory of why things happen yet, we see that neural networks can learn to create neural networks in a certain way. So
yes, but for the sake of the discussion, right? We don't like these handcrafted features anymore because they can be learned by the networks. However, we now need to define the architecture, which has parameters, let's call them handcrafted parameters. Now, if the answer is we can learn the network by using what you now call a hypernetwork, which I would think comes with a lot of parameters, what do we gain in the end? Is it less parameters? Is it more meaningful parameters? Is it more general parameters? So parameters which can be used for more different applications? Or why would we go from one step to the next and end up still having to set these things manually?
Yeah. So what you gain is a network, so the hypernetwork, that can generate multiple networks. So you train it once, maybe it will take really long, I don't know. But once it's done, you can generate as many networks as you want for different performance targets. So we gain this. Also, we gain time for grad students because they don't need to adjust parameters of the small students.
Yeah, okay. That's in a different domain. But when you say different performance targets, does that mean speed and memory consumption, or would it also mean things like accuracy or different applications? Because the ship you showed is, of course, completely different applications from having to classify, you know, a land image. Is that possible as well?
So both go together, right? Generally, if you design a lightweight architecture, it will have less accuracy than a bigger generally. So these metrics are all linked together. They form a landscape, and we need to create networks within that landscape. Right. So does that answer the question?
Well, it does. However, maybe it's impossible, but I would have looked for more detailed answers. A lightweight architecture with few parameters obviously does not have the same accuracy. It may, however, given that you want to do road extraction or that you want to do the forest layer and not ships in the water and not sheep on the grass or whatever, right? So it could be application dependent. And maybe this is asking too much. I'm asking you.
I think that this already exists. I'm not sure. So
well,
we need to look into it.
Yes,
I guess. But I think this could be done. You could create a hypernetwork and tell it, okay, I want a network with this size that does this task with this accuracy, and create a new network using that. I'm not saying it's easy, but I think you could do it. And this is where we are.
Anyways, let me look into the simplifications you have performed in your first task. Now, one of the things you did was you deleted the skip connections in UNet, if I understand correctly. Now, there was a good reason for these skip connections to be there. One is convergence of the networks, at least as far as I understand. And the second one is geometry.
Yes.
The networks, including geometry, including skip connections, are typically geometrically better. Now, cloud detection may not need the utmost geometric accuracy of your delineation of the cloud. Nevertheless, did you observe any of such behavior, less accurate results? Maybe also a difference in convergence?
Well, for cloud, not so much. I have actually have a backup. This is the impact of skip connections in CUNET and CUNET++. And so this is on cloud segmentation. And we find that there is actually no meaningful difference in the accuracy. So this is why.
Now, accuracy here is classification accuracy. Is that right?
Yeah.
No, I'm talking.
Pixel-wise segmentation accuracy.
Yeah. What about the accuracy of the delineation?
Sorry?
Of the delineation of the border, because that is, if you think about your road network, you know, you really have to have it on the ground at the position where the road actually is. Otherwise, you have a problem.
Well, I don't think we did that experiment because we saw that in the qualitative results that I showed in the slide earlier. There is no real difference between the delineation in our compact networks and the really big units. It properly follows the cloud, just like the big network. So we don't think, well, I don't think, there would be a difference when adding these connections. And this is what we see in the metrics as well. So yeah, this is why we remove them in the first place.
Final question on that topic. The application you had was cloud detection, and that your results are very convincing, no doubt about it. Now, if you were to do what I call classification, mind you, I come from the remote sensing area, and there is differences in terminology, as you probably know. So in your terminology, I would call it either semantic or probably instant segmentation, which is, of course, classification in the remote sensing case, of a land area. So you don't have two classes, cloud, no class, but you have 10 different classes. You're thinking about, not sure, any topographic data set. Could you still, do you have a feeling of what your compact network is going to do versus the more detailed network in terms of classification accuracy? I come also back to the geometric accuracy, etc. Do you have a feeling of whether these networks you have created would also work for much more complicated applications with many classes?
Okay, so I have tried CUNET with building segmentation. And for this task, it doesn't really do well, for example. So as I said in the conclusion slide before, it's too complicated for building segmentation task, because we need to precisely locate the corners and the facades of buildings. And for example, here the skip connections would really help, I think. So for these complicated classes, I don't think it will work so well. But from multi-class labeling, so if we wanted to label both the forest and the cloud, so it's fuzzy classes like this, I think it would still work. Even if we have to double the number of parameters, let's say go from 300 to 600, which is still not a lot.
I'm not sure how we are going for time. Am I to continue, or am I to pass over to somebody else, and then we'll have multiple rounds? Or what's the?
It's up to you, but you can ask other additional questions. No problem.
Okay. So whenever I have a question, I have to ask it now. Yeah. I get it. Okay. Let's jump to the last of your contributions, the road network task. I have two comments here. First of all, road networks exist for just about every part, every place on Earth. Now, and you have mentioned that in one of your slides, the real question is about updating. How would you do that? I mean, how do you incorporate prior knowledge of the existence of a road network somewhere?
Okay, so I thought about that. And okay, when we have our network like this, if we have prior knowledge of a map, we can force the existence of some points. For example, we generate the heat map here with the junction prediction, and we know that there is already a point in some place, so we force it to 1. We tell the network there is a point. And yeah, basically that's it. And we compute the rest of the network, and it will tell us which edges have been added or removed.
But the knowledge you have is a lot richer, isn't it? It's not only I know here is a junction, but I give you the complete network. It's consistent, it's connected, it's complete, at least at the time when it was created.
So the graph neural network input is also a set of edges. And we can incorporate this prior knowledge about the edges into the stencil of the graph neural network. So we can also use this. It's just a little less straightforward, but it's totally global. We know that there are some edges, and instead of initializing with the complete graph or KNN search, we could use the graph that we know.
And now we take it one step further. There's a very general problem in all these learning by example procedures. Namely, some of the examples are incorrect. Your training data are not 100% correct, and I'm sure you've come across that problem. How do you apply that?
In what part exactly?
Well, for instance, I give you that old road network. You just told me how you incorporate that prior knowledge into your system. However, of course, there have been changes. So some of this old network is incorrect. You know, roads have been added, so it's not complete anymore. And perhaps also some roads have just disappeared. So, of course, you don't know which ones. If you knew, this whole task would not need to be done, obviously. So you have incorrect or whatever training data.
So actually, my answer to the previous question, I already solved that.
Okay.
Because the graph neural network will predict the existence of an edge for each pair of points in the graph. So even though we start the message passing of the graph neural network on the graph on the prior graph, we can add or remove edges in the final graph.
Would you not need some probabilistic notion of some sort? Because it's otherwise you would run the risk to take decisions which are premature, perhaps?
But for each edge, the graph neural network will predict something between 0 and 1. So
okay.
It is.
So that you have that incorporated in.
It's a link prediction, and we use sigmoid on it. So
okay.
We have something between 0 and 1. So we can threshold. So we can design something a little bit more complicated. Like if we know that there was supposed to be a road, but the prediction is below this level, well, we delete it. Otherwise, maybe the network got it wrong and we keep it. We could do something like that. So I think it works.
Okay. Last question. When you introduced your method, you said there was nothing such things before. Now, there was, of course, road extraction in the pre-deep learning era.
Okay.
And there is, of course, work which would have modeled a road, for instance, as a bright line, you know, against dark or black background. It would model gaps, which would then be bridged. In other words, there was this connectivity idea, well, you call it a graph, you could just call it connectivity. It doesn't really matter. So that type of work existed. No networks, no learning, because we had models which would predict what the road should better look like. Do you have any sense or perhaps done any comparison with respect to what you do now? So you didn't do any comparison, but what would you, how would you comment? I mean, what if I tell you these old methods would at least perform equally well? What would be your counter argument?
No.
No, that's not an argument. That's just an answer.
Because the first deep learning based methods that I'm comparing against were already performing much better than these old handcrafted methods. So
no, not necessarily for the task of road prediction. I think we need to be more detailed, maybe.
So yeah, I haven't looked at all the prior work on this. So, but I know that modern deep learning based methods outperform these old methods by large margins. So,
in general, they do. I agree, but that's of course a very general statement.
So this is why we haven't really looked at it.
Fair enough. Okay, I'll stop here. Thanks very much.
Thank you.
I'll
Thank you.
pass on to whoever is next.
Thank you.
Thank you.
Thank you.
Let's continue. Let me turn on the sound. Professor Sébastien Lefèvre.
Yes, thank you, Mr. Chairman. So thanks for the invitation. Is the sound okay? Do you hear me correctly?
Yes.
Gaétan?
Yes.
Yes, and the jury as well, yes.
I'm trying to put you on the screen. Windows.
Okay.
What the hell?
Yeah, we will display you on the screen.
Okay, great.
Really hard. Like, oh my God, why?
Okay, so first of all, sorry for not being with you today. I would have really appreciated, but okay. So Nice is far from okay. Hanover is also far, but you had a good reason to come as well, Christian. But yeah, it's quite far to reach Nice. So sorry for joining online. But thanks for the invitation for this jury and for giving me the chance to assess your manuscript. So I really appreciated the topic you were dealing with. So of course, deep learning for Earth observation is a very important topic. It is widely explored in the community, and I really appreciated that you take a different angle to attack this problem with this embedding ability on the satellites, and this makes, I think, most of your work very different to yet another network that will try to get 0.1% more of accuracy. So this, I think, is really interesting. And I was also impressed by the quite large range of contributions. You address very different problems in the 4 chapters. So I was a bit surprised that you managed to cover all these different contributions in your talk. So I was expecting maybe you had to cut and to focus on some of them, but you managed to present all of them in time and with a clear presentation, as it was already said by the previous reviewer. So congratulations for this.
Thank you.
And I also have some questions, of course. And I have, okay, some of my questions were already addressed partly by the previous reviewer, but so maybe I will skip some of them. Anyway, okay, let's move. I will start with the first chapter with we already discussed about your UNet variation and the skip connections. So on the slide 11, if you can, when you introduce your specific architecture, I was wondering. So if you just okay, when you see all of these, and when you see at the end your C UNet ++, do you think it's still a UNet basically? Because Okay, as it was already said, but then you remove the skip connection. That was actually for me the main contribution of the unit. So is it worth calling this unit something, your network?
This is an interesting question. Well, we started from a unit, so we called it a compact unit. But yeah, it's not really a unit anymore. So it's a different thing. And I think I would, I wanted to call it something else, but just saying C unit was more catchy. So we left it like that. But no, I don't think it's a unit anymore.
Okay. Yeah, okay. For me, when I look at your architecture like this, I think it looks like more segnet. So it's an encoder-decoder architecture. You don't have the skip connection anymore. So maybe it's a bit of yeah.
So segnet also
yeah.
has some kind of skip connection. In segnet, we keep the pooling indices.
Yeah.
Them in the decoder. So it's already well, it has some skip connections. The C unit we designed would be more like a deconvnet, which is less known than segnet or unit. But if you look up deconvnet, it's actually pretty close to C unit.
Okay, so maybe it would have been better to really relate your methods to the real close one, because then when you compare your C unit plus with a unit, of course, your model is much simpler. You actually removed most of the DNA, I will say, from the unit, and you still have. So okay, you show that you reach about the same accuracy, but maybe the problem actually you were tackling, and I think it was already said by the previous reviewer, the segmentation problems you were tackling were probably too simple too simple, and maybe didn't need actually a complex network like a unit, because when you deal with cloud segmentation or fire segmentation, do you really need geometry? It was a question that was asked, and I fully agree that it's not really, I'm not sure the spatial information is very important there.
Yes, I agree.
Okay, so
however,
okay, I see your okay, this slide as well. So
yeah, I was just showing that there was already a network based on deconvnet that was called mock deconvnet. So we would have called it C deconvnet. So yeah.
Okay.
I don't know.
Okay. Maybe a question. Okay, on this part. So maybe one question related to the way you did your research in this chapter. So you, at the end of your study, you conclude by the fact that okay, it's very important to engage into neural architecture search in order to avoid some manual so uncrafting not the feature but the architectures. You were asked about the theory that is behind such kind of automatic mechanisms to simplify maybe a network. I was wondering, in your own approach, how did you end with your C unit plus? I've got the feeling that it was very empirical. So were you relying on some well-established knowledge or theory, or could you explain a bit more your intellectual path that would that brought you to this choice at the end?
Okay, so it was mostly empirical, but most of the decisions had intuition behind them. So for the removal of the skip connections, for example, it was already explained. We didn't think we needed high frequency information in the decoder part for cloud segmentation. So we removed the skip connections. For the removal of convolution stages, well, stages exist because we need pooling to aggregate local information to take a local decision. And for clouds, we found with the team at IRT that we could do cloud detection, cloud classification with only 22 by 22 squares, something like that. So we designed CUNet and CFCN such that they have a similar field of view, because we knew that we could classify clouds with that field of view.
Okay, and and in this context, you still need a semantic segmentation network. I will say a standard CNN on these small patches was not enough.
No, it's not enough, because, well, it is enough for some applications, but patch-based classification is less granular than segmentation. So it is, in the end, less precise. But of course, it also works. It depends on what we want to achieve. So, for example, if we want to precisely estimate the cloud coverage, semantic segmentation will perform better. But if we want to remove the cloud pixels for transmission, it's important to do segmentation, because a patch-based classification would discard entire patches if they only have a small part of cloud inside of them. And the data that is transmitted would be incomplete. So semantic segmentation is more adapted to this kind of task.
Okay, yeah, I'm okay. Not fully sure to agree if actually the patches are small. If the patch is large, yes. If the patch is small, okay, it's. I'm not completely sure, but anyway.
But
okay.
Really small when it just becomes semantic segmentation.
Oh, you don't actually. You can just do. You can just use an encoder like a standard CNN, and you don't need the decoder part. But
yes,
if you maybe you don't need the pixel level accuracy. Anyway, okay. One important thing I noticed in this chapter 2, that I wrote in my report, was the way you use your test set. So I would like to have a discussion with you about that, unsurprisingly. So if I don't know if I'm not sure you were showing these slides, but I think you understood you understand what I mean regarding. So it's in it's page 31, I think.
Page 31. I don't have the manuscript.
Okay. Anyway, so what I can from what I understood, what you in your experiment, what you did was to divide your data set into training, validation, and test, doing several shuffle and split. I mean, the training you split it correctly between training and validation. So you end with different models, and you tested your different models on the test set. And what is for me a bit to be discussed is that you wrote at the end of all rounds, the best network for each architecture is selected using the test set.
Yes.
So when I read this, I was thinking, we need to have a discussion about that.
Yes.
Okay. Do you think this is fair from a machine learning point of view?
Okay. There are multiple parts to the answer. The first part is that no, it is not ideal for machine learning point of view. We should not do this. But from a fairness point of view, you mentioned the word fair. We did this experiment similarly for all of our networks and the competing networks. So the final evaluation stays fair. Okay. The reason why we did this in the first place is because these networks are, that we design are so small that they have a lot of dependency on initialization. If we only have 300 parameters, if we have a bad initialization, the network might not learn at all. So for me, it was important to have more rounds of training and select a good enough network for evaluation. And this was done on the test set. I admit this was a mistake. I should have done it on the maybe on the validation set or a second separate validation set. This is something I cannot correct now, but I admit it should have been done differently.
Okay. I'm glad we agree. And yes, probably the fact that probably using considering your training set into training plus validation, and then the training as training plus validation again with some shuffling, and using your validation first level of validation as what you did with your test set was probably a better approach. And especially the issue there is then that you can you report. I understand that you're fair between your different methods, but then if I read your if I look at your result, I would say, yes, you reach this amount of accuracy, this accuracy level. And if I compare with other studies on the same data set, then the results are not comparable because you optimize on the test set.
Yes.
So you raised a very good point about the low number of parameters. So this is something that is very appealing to have a lighter network. And so what you are saying is that, okay, it's good to have a lighter network, but there is a risk of an incorrect initialization. So have you done specific studies on this topic? I am not sure I found, okay, I haven't noticed anything on this in the manuscript or in the talk today.
No, this was all empirical in the experiments that we performed. We saw that sometimes the accuracy would be really bad because of the initialization, and running with a different seed for the random number generation would get a better result.
Mm-hmm.
So it's not really mentioned in the manuscript, I think. Maybe I should have mentioned it.
Yeah, I think actually, if it is a bottleneck of a light network, then it calls for further study to be sure that you can actually adopt these lightweight networks in real applications. Okay, let's move to the second chapter, where you actually show that your 1D convolutional LSTM performs well. I think you had one. Okay, let me see. Where was it? Probably it was slide 26. At some time I was just missing a point. Probably. Was it this one?
This one?
Okay. 26 line by line. Okay, no, maybe it was just before then. Okay, I'm not sure you understand. I missed. Okay, maybe slide before then. Okay, and then the one before. Sorry. No. Okay. Oh, okay. You will answer anyway. So in this chapter, you propose some architecture dedicated to the Bushbone sensor, and I think this is very. I mean, it is highly relevant. But maybe, okay, you should correct me if I'm wrong. But what I understood is that you show that with a CNN or a convolutional LSTM, so not a CNN, 1D convolutional LSTM that works on a single line of pixels, you get an accuracy that is similar to what we can get with a 2D semantic segmentation network. Am I right, or did I miss something?
Yes, that's right.
Okay.
Surprising, but that's right.
Okay, so in some way you are saying that okay, for semantic segmentation we don't need 2D spatial information, 1D spatial information is enough.
No, I'm not saying that.
Okay, okay.
What we saw, let me show you the slide here. What we see here is that 1D is not enough because we have run a 1D convolutional network experiment and it performed really bad compared to the other networks. The 2D information in the scanner net with the recurrent neural network is contained inside of the network in the internal state. The internal state of the network, we've retained the 2D information. So the scanning creates the 2D information, I guess.
Okay, okay, I got it. Okay, in the memory of your recurrent neural network, you actually store features from the previous line.
Yes.
Okay, okay, this was not very clear. Okay, so sorry for my misunderstanding. It was not very clear this part. Okay, have you compare with different buffer in terms of spatial, so the field of view, the 1D field of view that is contained in the convolutional part, and on the x-axis, and on the y-axis, that is the temporal buffer, the number of lines that you can buffer in your network. Have you explored this?
Yes. So for the width part, the bigger scanner net that we design uses 9 pixel stencil, and the small one uses 7 pixels. Also, the bigger one has a larger memory because this is the F1 and F2 numbers in the table. We use more filters in the bigger scanner net. So it should be able to retain more information. We do not actually control what it retains. So it's not a buffer in terms of number of lines. It's the network chooses what it wants to keep in this memory.
Okay. Okay.
Gave a larger memory to the big scanner net.
Okay. Okay, I see. Good. So I think on these two problems that okay you do so you apply semantic segmentation techniques for I will not say easy remote sensing classification problems, but actually maybe problems that could be solved also maybe without deep learning because for both fire and cloud detection, maybe we don't need that much about the geometry, for instance. So I really recommend that you consider more complex problems like either binary problems like building extraction, or as it was suggested by your previous reviewer, multi-class classification that are, I mean, land cover classification typically to see how your network will behave maybe a bit on more complex problem. Okay, if I move to the next chapter. Okay, so I found it very interesting as well to deal with contour regression and to think that okay, instead of trying to have just a better object detector or better method for instance segmentation, then it is very important to provide compact output. So this is this is a problem that is not well studied, and that is very important, I think, for embedded applications. So it was very interesting, but I was a bit disappointed by the fact that actually you are dealing with some standard computer vision dataset. You are not dealing anymore with some remote sensing dataset.
Yes.
Why is this choice?
Okay. So in order to publish in computer vision conferences, we need to compare ourselves using these standard data sets. And for the numbers that we have for all of the methods, so FourierNet, ESESeg, Polar Mask, Solo V2, PINet, etc. We have numbers and we have implementations on these standard data sets. So Coco, Pascal, VOC, and that's it pretty much. So if we want to compare correctly against these methods and to do it in a fair way, we would have to re-implement all of them and retrain them, all of them, fairly on remote sensing datasets. So this is a huge task, and we only have so much GPU power at our disposal. We have a lot, but we cannot do everything, basically.
Okay.
So we have not tried our contour regression method directly on remote sensing datasets, but we are confident that it could perform just as well as on Coco.
Okay. I understand the difficulty of comparing with other work. So of course, providing code as I mean, it's much easier today to compare with related work than it was a decade or two decades ago because of the code availability. But it could be an issue if actually you have to retrain the model and maybe to set some hyperparameters and this kind of thing. Anyway, since your PhD focus on on EO data, still, I think it would be interesting to discuss about so maybe not a comparison with related work on some remote sensing data, but at least to be able to assess the behavior of the method on such data. And before that, I mean, with the global, the main question there is, do you think the objects that you could have to deal with when you are a deep network on a NEO satellite, do you think the objects that you can observe have the same shape than the object you can have in Coco? So you see, is your method applicable to such kind of objects?
I think so, but we would have to carefully look at what classes we want to use this method on. So on examples such as boats, this method could work really well. Or planes, for example. We have some images of planes in Coco, even though they are from the side, the method works and is able to find all the tail of the plane and the wings. So it would work just as well from above. So for stuff like cars, planes, boats, and etc., this method could be applied. I don't think it would be ideal on classes such as individual buildings because they have square corners. So we would need to use a different method. Or if we have large objects such as a whole forest, this method doesn't really make sense for that. It makes sense for individual objects that we can clearly separate from each other. So I think it's applicable. We need to find the proper application.
Okay. Okay. So then I fully agree that for some kind of small object, I mean, simple objects, I will say, not compound objects, but simple objects, the method makes sense, and you can rely on, there are some public datasets. So it's very easy. I mean, there are plenty of datasets Okay, most datasets are on object detection, so maybe they don't have the exact ground truth, but there are some datasets with instance segmentations, and then in this case you can extract the contour and you can have some ground truth and train your network and to assess it. It's also true that for buildings, probably the way you simplify your model actually the contour by some curves, I think is not relevant, and it's not really also compliant with what we expect from a GIS, as you said in the chapter on the road graph. So for building, it's maybe not the good approach. Do you see? Okay, let's go into this question then. If I would like to adapt your methods to deal with buildings, so I want to directly extract buildings in an area. And I would like to use your methods or an adaptation of these methods to be able to extract building polygons. What can I do? What is needed for your methods to work on such a context?
Well, first, you can try it just like that. I said it's not ideal, but maybe it will work. If we look at some examples here. Here, we see that the network can find some really sharp parts of objects. For example, the tail of the birds, the tail of the plane, or the legs of the tennis player, or the racket, tennis racket. So maybe it can work if we train it properly. Maybe it can work for buildings. What I would do is augment the ground truth. So usually buildings, they are the ground truth for buildings is a single point on each corner of the buildings. But I would densify that so that this network can properly learn on them. So I would create maybe, I don't know, 128 points for each building by densifying the ground truth. And maybe we could learn to find straight lines. So this is the first thing I would do. Just try it as is on buildings. Does that answer the question?
Yeah. But then, okay, I understand that maybe then you can extract some contours that you still regress with your Fourier coefficients, but then still it is not compatible with what you could how you could feed a GIS. But okay. Maybe on this part, I have a question related to the evaluation metric you were proposing, what you call the overall efficiency score.
Yes.
I was a bit doubtful about the justification for this and the soundness of this metric, because basically you compute a product between measures that are not related one to the other and that are not scaled, not normalized. So do you think it is relevant to proceed like this?
We needed a score that was computed using the three metrics and what was easy to understand, basically. I tried different things. I tried normalizing every score, but then it made it really hard to explain in a paper. So this is why we ended up with this simple metric. And I think you're right. I agree that it's not the ideal metric for what we are doing. But it's a simple one. And I think it represents the overall efficiency quite well. Yeah.
Yeah, I understand, but in the same time, when we look at the equation of this overall efficiency score, where actually it's 100 times the mean average precision times the frame per second and divided by sec, and I don't remember. So the size of a single detected object in memory. So everything is not normalized, and I think there is a strong bias. towards maybe the values that have the highest range in terms of absolute values. So I will be very careful in the analysis of this. And I think you could have used more harmonic means or normalization of this. So yeah, or also literature in okay, there are some methods that allows you to compare different. So there are some techniques that allows you to compare different methods with a set of criteria, and so you at the end you say, okay, finally this method beats the other one in terms of or rank first or much better than all the others for this amount of criteria, so it is better. So there is some literature on this, and I just have to remind the method. But yeah, okay, there are some better methods, I think, probably to deal with this.
Yeah.
Okay, I think my time is almost over. If I may, maybe I will end with one or a couple of questions on the last chapter. If
Sure.
Okay, thank you. Okay, I mean, okay. So on this last chapter, okay, I have the same remark regarding the metric you are using, but okay, I will not go more into this. Maybe one comment regarding some result between. Okay, so let me just find back the page. Okay, it's on. Okay, you did some comparison of your methods with two different backbones. So using ResNet 18 and ResNet 50. So of course, in the context of embedding the network on the satellite, you should go for the simplest backbone as possible. It's easy to understand.
Yes.
And I was assuming that actually using ResNet 18 instead of ResNet 50 will really greatly reduce the time you need during inference. And finally, it's not the case. It's 19.6 versus 20.9 seconds. So for me, it means that your backbone has a little, very small influence on the overall complexity of the model.
Yes.
And what does it mean? Do you know where is the bottleneck in terms of computational complexity in your approach?
Okay. So I think the graph neural network part has a bigger complexity than the encoder part. So when we took the ResNet 18 and replaced the ResNet 50, it didn't make a significant difference because the rest of the network has a bigger influence on the running time. So this is the explanation. But
Okay.
also, what this means is that even though ResNet 18 will compute a low quality feature, we can still use it. So we could use a really small backbone, and this would make our network better for embedding on a satellite, for example. So
Okay.
the bottleneck is actually later in the network.
Okay, so but the data is smaller because you operate on the graph, but then you have more computation per node somehow than computation per pixel. That's what you mean?
No, I'm saying it's actually the same computation for both ResNet 50 and ResNet 18.
Yeah.
Look at this figure here. The ResNet is only this small part left. And all of the rest of the network is the same. So if we reduce the size of the ResNet, well, we reduce the compute by a little, but the rest of the network is still as big.
Okay. Have you assessed the time or the complexity of your different components?
Not really.
Not really. I think it will be interesting also, especially if you are in the process of having such a network embedded on a satellite. Of course, you optimize everything, and you have to think, okay, where the memory, the energy is consumed, and where you should optimize.
Yes. But
Okay.
I think we can still optimize this network further. Again, it's a question of limited time and limited compute power. We could have done some neural architecture search on the middle part of the network, but we just went with something that works. We found that 3 convolutions for each branch worked pretty well, so we used that. And maybe we could get away with less. Same for the graph neural network. We could reduce the number of layers. We could maybe we used too many filters, etc. So of course we can still optimize it. What was important for us is that even though we didn't take the time to benchmark or profile every part of the network, we still beat the others by 100 times. It was 100 times faster than the state-of-the-art network. So it was already a win for us. And we didn't spend much time optimizing further.
Okay. And so maybe an opening questions to end. So you had worked a lot on adapting the architectures, designing some novel architectures that are more lightweight or provide either more lightweight in terms of their inference, or providing lightweight results in terms of compactness of the output. So it is one important problem if one wants to embed deep learning in Earth observation. So if you have to tomorrow to restart a PhD or to supervise a PhD, or let's say with IRT Saint-Exupéry, a new PhD on embedding deep learning on Earth observation, what is based on your knowledge that you have acquired during these 3 years, what is now the most important problem that prevents deep networks to be embedded in operational settings on satellites?
The main 2 things, I think, are tools and explainability. So tools are actually really important in this kind of work. When we want to use a network like this on a satellite, well, we need to convert it, make it run for the chip that is inside of the satellite. And we actually lack tools to do most of this. When we use complicated architectures, we will always get, oh, this operation is not supported. Oh, this doesn't work. Oh, this is broken. And we need tools, actually. We need to focus on ways to grab a network that works and compute, properly convert it for each possible target. This is really important. Otherwise, we will never be able to use them. The second part is explainability. This is, I mentioned it in my conclusion, but I think this is really, really, really important. No one will let you use a neural network in production if you cannot explain what it does. And if you are not sure of how it will react in an uncertain or unseen scenario. So these are the main 2 things, I think.
Okay. Thanks for all the discussion, and thanks again for the work on the invitation.
Thank you, Sébastien.
Now, Adrien Girard from IRT Saint-Exupéry.
Okay. Well, thank you, Gaétan, first for your work you've performed on the CR project. And thank you also for your presentation, that I found very interesting and very didactic. I have a few questions, maybe less technical than the two previous person, but I will start with the first use case because I think it has been already been mentioned twice, but on the cloud segmentation use case, I think it would have been interesting to test other methods and also methods that are not deep learning, because that's, I think, problems that can be solved with more classical methods. But my question then is more general. During your PhD, have you sometime met a situation in which you thought that it would be interesting to add some a priori knowledge in your models in somehow to improve the performance? Because from what I understand, all the architectures that you've made during your PhD are heavily based on data, and so is there a point during these last 3 years, or when you thought we could do better with some a priori knowledge?
Yes. Just 1 second. I will reactivate my microphone. So can you?
Go ahead.
Is it okay now? Okay. I can talk like this now. Okay. So typically for this network, I think it would be really interesting. Christian mentioned it during the questions. It's a network where we can incorporate this knowledge really easily. We can add points that already exist. We can add edges that already exist. And in that case, especially for the map update problem, this is really interesting. For the cloud segmentation, I don't know how we would have a prior knowledge like this. So I don't really know if it's applicable. But you mentioned working using non-deep learning based methods, and I think we run those experiments at some point. I just need to find them here. Okay, I don't have them. Sorry. But we compared the output of our networks to FMask, which is a cloud segmentation method, which is not deep learning. And we found that our method outperformed this classical cloud segmentation method. Okay. So we tried it. Okay. But we could use both, actually. We could, if we have enough bands for FMask, because this is not the case on OPSAT, for example. There are not enough bands to use the FMask method. But if we have the bands, we could combine FMask and a deep learning method, for example. So we can use it as prior knowledge. For the contour regression, I don't really know. I would have to think about it. Okay. We use geometric priors for this method. We have the prior knowledge that the network should circle the objects once. This is a prior knowledge. We avoid the self loops by using a prior knowledge as well. We have the knowledge that we should not use too many high frequency Fourier coefficients. So in a way, we've already used the prior knowledge. Okay, I didn't know that you tried the FMask on the. Yeah, the numbers are in the paper. I thought I had a slide, but because this is a comment I already got twice or 3 times while presenting the CR project, and your result is. Oh, well, why do you do deep learning on that? Do something else? Well, yeah, FMask is just not as good. and it requires more bands. I don't know the number anymore, but we only work on RGB, and we could not use fmask on offset.
Okay, on your second chapter, ScannerNet, if I understand well, the convolutional part is using 3 bands RGB in your model.
Yes.
Most of push-pull sensors actually only have 1 band. The three color image is reconstructed later in the image processing chain.
Okay.
So do you think your ScannerNet could be adapted to work on 1 band for sure, but to work, for example, on slightly unregistered band or bands with different resolution, for example?
Yeah, I don't see why not. This information is shuffled inside of the network anyway. So let me show you this one slide. When we use a filter size like 7 or 9, the network can learn, especially with 2 or more layers, to think of the bands as registered. So I think it could work with that. Maybe you would need to add 1 more layer, maybe, or widen the filters to 11 or 13. It's not that much more computation, but it could work.
Okay.
Yeah.
And on the subject of the bands, I think I read in your manuscript somewhere that you think all the architectures that you propose are adaptable, can work on systems with more bands. Would you say it would still be okay with hyperspectral systems with hundreds of bands?
Okay, this is where you use the prior knowledge, because you know which object, which kind of the object, you want to detect. So you can analyze the hyperspectral cubes and find the bands that are more relevant for these objects, and then only work using these bands. So you can incorporate prior knowledge about the objects like this. And then use the architectures as is, as they are. Yeah. We could think of ways to compress the hyperspectral information by designing some kind of network that would maybe take all of these bands and understand what's important. We could learn that part too, maybe. Learn this prior. I don't know.
So on your third chapter, the control regression, I understood when I read your manuscript that one of the motivation for a compactness representation, a compact representation of the object, was to go after change detection, onboard change detection.
Yes.
You write somewhere that you haven't had the opportunity to finish this pipeline.
Yes.
What would be the next steps to achieve this onboard change detection based on your method?
Okay, so the first step is compression. We need to analyze properly the outputs of this network and find which Fourier coefficients we can set to 0 in order to compress the regressed shapes. Then construct an onboard database. So if we want to detect boats or planes or whatever, we need to store their localization and shape on board in this database. After that, on the next acquisitions, we can find if the objects are still present or if they have moved, if the shapes have rotated. we can match the size of the shapes. If there was a small plane, maybe now there is a big plane, so the plane changed. And we can work like this to perform change detection on discrete objects.
Okay. And do you think like the Fourier coefficients would be sufficiently precise to describe the object? Do you think we could really like find match between objects?
I think so. You could match a type of plane, or maybe not tell the difference between a small Airbus plane or a small Boeing plane, but we could find that it's a small plane, and the class would be small plane. You see, so maybe it's not as precise as we would like for maybe discerning like every little part of the objects, but I think it's good enough to start, at least. Then we can think of some other way to retain interesting information if we need to. So we could use some features that would be added to the contour regression head. So, for example, we tie the shape with a vector of features that describes the object in more detail. We don't know what it would be, but after that, we could try to learn to differentiate between different objects like this. So we can add some stuff to the method in order to make it better for this kind of task.
Okay. So on the last chapter on word extraction, we already talked about that, but I still have doubts on your operational concept on flows and everything. I think in disaster situation, you can manage to find a real person to watch after the image and identify where are the roads. But I think you have other operational concept in mind for this algorithm. Could you elaborate more on this other concept?
First, I want to go back to the first part of your sentence.
Okay.
You said that we can download the image from the satellite and have a real person identify which roads are still usable, and then tell people which road to take to escape. But I think it's too long. I think it's really too long. Using a neural network like this on board, we could download the map directly from the satellite to the GPS of someone. So let's say I'm evacuating this place. I need to get out. I'm in my car. Oh, I have an update from the satellite for my GPS. I know where to go now. You see, this is important stuff. And not only in floods, but earthquakes or defense applications. So sometimes we cannot wait for someone to identify the possible roads. And this is the point of our method. Then for the second part of your question, there are some other applications that we could perform using this kind of method. And it's all based, well, most of it is based on road attribute regression. As you see in the method here, we have a graph neural network, and it can identify if a road exists or not. But we can add more things, more outputs to this graph neural network and regress road attributes. So we could do all kinds of things, actually. We could infer traffic density, road speed, what type of road it is. Is it like, is it a highway? Is it a dirt road? So we can add more things to this method. And also, we already mentioned it, but the map update problem is something that we could do here.
Okay. about the map update. Don't you think like a method based on an existing network, and for example, just a regular change detection based on radiometry, for example, saying, okay, there has been change on this road, would also work as well or even better?
I don't know. You should try it. I actually don't know. I think it would be very optimistic to think that simply looking at radiometric information could be used for map update, because let's say it's the winter and there is snow everywhere. Oh, but the radiometry has changed a lot, but maybe all the roads are still there. So I don't know. I think maybe we could try, but it is clear that it's not that simple to me.
Okay. So now I have a more transverse question. Because you mentioned that you run your almost all your networks on embedded targets, hardware targets. So I think you already mentioned that tools were an issue.
And you know it.
Have you also noticed any? Because I guess all the accuracy, performance you give in your slides and papers are computed on server to be comparable with papers. Have you noticed some loss in the accuracy once you run the network on the hardware target?
Okay, so we looked at that for the semantic segmentation problem. I don't think I have the slide here, but if you look in the manuscript, there is a graph where we show the loss of accuracy when quantizing the networks. And so we have looked at it a little bit.
Okay. I know the abstract case, but I was more thinking of the other use case, like the one for road extraction or contour regression. Have you noticed some loss in accuracy?
For the contour regression, I don't think we have looked at the accuracy of the networks on target. Yeah, we just looked at the speed, but yeah, it was quantized to int8. So you would have some accuracy loss for sure. I don't know how much, but it would be typical of what we do when we found, well, what loss we get when converting to int8. There is always a loss. So when you quantize a network like YOLO, for example, you would get the same accuracy loss pretty much for our network, because we use the same backbone, for example, and a similar type of head. So, yeah.
And maybe a last question. Among all the use cases you worked on during your PhD, what would you say among all these contributions? What would you say? What is the most valuable to your field? First question. And second question: what contribution do you think has the most chance to fly one day on an operational satellite?
Okay. So for the first part of the question, what is my field? Is it remote sensing? Is it computer vision? Is it computer science in general?
You tell me what.
Okay.
From an academic point of view, or for a more theoretical point of view, what would you say is your most valuable contribution?
Okay, I would think it's the road extraction method. I really like it. It's my favorite of all the projects. I think it's really cool. It's really different from all the other methods that came before. So I would pick this one. I think ScannerNet is also pretty interesting. It's not as impressive, I'd say, but it's still an interesting thing to see. I actually looked and no one thought of this before. Like, let's do 2D segmentation with a 1D CNN with RNN. No one thought of this. And it's pretty interesting for the field of embedded computer vision, because it will save a lot of memory, a lot of latency. And so it's a valuable contribution for different fields. So yeah, that's it.
Okay. Thank you very much, Gaétan.
Thank you, Adrien. So now, Yuliya Tarabalka from Lefèvre.
I also congratulate you on this extensive work during 3 years. So indeed, as my colleagues told, a lot of very different, interesting contributions.
Thank you.
Just a few extra questions. So I also start with chapter 2. You mentioned that you tried your compact networks on building segmentation and it didn't work very well.
Yeah.
So today, with all your knowledge, if you need to design some lightweight network for buildings, what would you do?
For building segmentation?
Yes, like for embedded segmentation.
Okay, I think I would take maybe I would start with a small unit like we have, but add the skip connections again, and so build a small unit and start with that, and then maybe take one of Nicolas' methods and try to make it more efficient and smaller. So work on something similar to that. If it's really for building extraction, I think we can also use the road graph extraction method. We don't have performed really in-depth experiments on this, but we showed that it can be used for polygonal building extraction. We could modify this method a little bit, and it would probably work better for this task as well. So yeah, either do something like Nicolas Girard, or adapt this to buildings.
Actually, that was like my next question. So it's very good that you
yes.
like the slides, because so like, yeah, I wanted to connect chapter 2 and 5. So, but so if you take your kind of like all your developments in chapter 5, which, as you just told, you are very proud of, but do you think it's enough lightweight, or like what you should do to like probably even make it more light in terms of weights, memory, etc.?
I think it depends how light do you need it, because to me it seems like it's already really lightweight. For the huge images of 8,000 by 8,000 pixels, we only take 20 seconds. But for a small patch like this, it's really instantaneous. So I think it's enough as it is. If you wanted to reduce it even further, I would do what I said to what I answered to one of the questions before. I don't remember who it was. Sorry, but I would do some kind of neural architectural search on the different parts of the network in order to optimize them and make it more lightweight.
Okay. So for chapter 4 about representations, and it's also like linked to all these previous chapters, because yeah, like it's a very interesting work in general for like computer vision. But if you take indeed like your topic of embedded, basically on satellites, artificial intelligence, like, because I was thinking like which objects, which classes it could be useful for, because even like already this question was asked and you told that it could be ships or planes, but like for operational reasons, you could also just ship and play. You could model it as, you told it yourself actually, like in different questions, that you could just model by lengths, widths, or like plane, you could even like directly because you told that you could to the contour add additional attributes, but you could just directly predict the class of plane, for instance, because they're all like limited.
Yes.
So a question like, what do you still think? Are there any, like, is there any class that would really benefit from this Fourier representation? Because I mean, if I take like this building example, it's much easier to model like it by 4 corners than to kind of store all these coefficients. It was also discussed earlier. But what would be the object, the application that would really be interesting for like for embedded artificial intelligence?
So on satellites or not?
On satellites, yeah. Like,
on
so
satellites.
Like how this work
Okay.
on contour regression could be useful for some satellites.
Well, yeah, ships and planes. No, really. Stuff like that, or other types of moving vehicles, like for defense applications and stuff like that.
But do you think that the defense is so important to like how to say, to stand down Earth the whole shape of the plane instead of just quickly sending that okay, it's a plane and
yes, because we can infer a lot of things from the shape of the plane. If we spot a plane using a satellite, the plane could be flying or not. So using the size, the relative size on the image of the plane, we can estimate its altitude. We can look at the direction where it's going, and it's interesting information. So it's not only the position, sorry, of the plane, and a bounding box would not be enough. So it's because it's just a square. We don't know where the plane is going.
But then you mentioned both mobile objects. So and then you told in the very beginning of your like chapter and presentation that this representation, unless I understood, misunderstood, that it's more like for change detection, that you will save this representation on the like satellite. So do you plan to store all the mobile objects as maps on your satellites?
Well, it depends on what you want to do. But yes, for change detection, we would need to store all of them, or all the important ones. Does that answer the question? I'm not sure.
Yeah, I mean, that's your answer, yeah, sure. Yeah, so for the chapter 5, it's a very little question also, like which already complements previous asked, because also like we know for roads that we have indeed like road network already, but then like when you, especially when you talk about embedded systems again, so when you will use your existing road networks, you will necessarily have misalignment, right? So basically you have like image that you want to run detection on, and then if you take your previous road network, you have quite strong misalignment actually.
Okay.
How do you propose to deal with that?
So the question is, I have an existing map.
Yeah, that you would like to update with your network.
I have a new image,
yes.
And I want to use the previous map to know which.
Yes, you want
nodes.
basically
Okay.
what like I think Kristen asked you. So you would like to like enrich your method in chapter 5 to be able to take the previous road network into account.
Yes, but misaligned.
But for sure, always it will be misaligned. I mean, because of like calibration, etc. Issues like you will never have it aligned. So what do you propose to do with that?
Okay, so what we can do is perform an inference without looking at the previous map. So we get a basic graph, then we align the previous graph with the new graph, then we perform the inference again to know which ones have been added or removed.
Okay. And don't you think that you can do it in one shot?
Okay, do it in one shot. I don't know. Maybe, but we would have to think about it. Yeah, in one shot, I don't know actually. In any case, it's still, well, if you train your network well enough, and the inferred graph without the prior knowledge is good enough, then if you realign the both graphs, so a single inference, the added edges or missing edges should be a simple matter of change detection between the two graphs. So yes, you can do it in one shot if the graph is good enough.
Okay.
I think.
Yeah, just like a very also general question, because it was already been asked, but is any of your work will be directly like beneficial for CR? I don't know if it's like Thales or ERT, like, so is it, is there any plan to industrialize the part of your work? Do you know that?
I don't know. Maybe Adrien can answer this one. I don't know.
I can say that all the work on the segmentation has already been used extensively on upsets for our demonstration on CR. And for a more industrial point of view, that was also why I asked the question about what you think was the most valuable contribution. What thing would have the more chance to fly one day? I think ScannerNet is a really interesting concept for push beam sensors, and I can see that working on a actual satellite.
Okay, and I can maybe complete this answer, but it's maybe not about Thales or IRT, because I work for some other people now, and they are interested in these methods. So I think also in your company, you could use a network like the one I have designed in chapter 5, 6, the road extraction method. I think it's useful for you, for example. So if you want to use it, go ahead.
Okay, yes, I stop here. Thanks and congratulations again.
Thank you.
Thank you, Yuliya. Okay, so my turn. In fact, I had initially 7 questions, but some of them discussed already. First, I want also to congratulate you on this nice piece of work that altogether form an extensive work. And I think also I'm impressed that you could do that in this madness of pandemic times, where
thank you.
For a team, I think it was much more difficult. Okay, my question relates also to RNN. You mentioned, I understood that this line scanned, so you process line by line, but
yes.
Is that the order of the line scanning important, or could you do that in a manner that it's like hierarchical or like interleaved in a manner that take more advantage of the context, that you first get the global view and then like, or do you do that in serpentine order or just line by line from left to right?
It's not really from left to right, because we consider the whole line as acquired at once. So maybe the satellite, well, for a push broom scanner, we acquire the whole line at once. So we don't scan the line, we have the line, and we do it line by line. So
could you ask do you think it would help to process them in a different order?
But why?
Yeah, because suppose you have very many lines. Okay.
Yes.
If you scan them top to bottom.
Oh yeah, I see what you mean.
Then you get only a partial view of the context. But if I give you only, like, let's say 3 main lines, that give you maybe another view of the image before.
Okay, that's interesting. I had not thought about it before, but I think you could skip lines, like really easily design an architecture that can skip lines. Let's say, oh, I don't see anything in the first line, okay, I will, in the first lines, I will skip 5 lines and not process these ones. And if I find anything in the next lines, oh, maybe there was something, and go back and analyze these ones. And I don't know if it would necessarily be more efficient. We would have to train it really well. And it depends on the application, of course. But I think we could do it with a reinforcement learning approach. So have a subnetwork that predicts how many steps we are going to skip at every iteration of the RNN. And yeah, we could do it. And I think it's an interesting idea.
Yeah. Okay. So again, relating to this RNN and scanline concept, are you finalizing the current line? You finalize it after you process it immediately? Or do you wait that you have scanned on the line in order to finalize this binary image?
No, we output it right away. So
right away.
We ingest one line and we output one line at the same time. You could.
But you have the memory from the previous lines, right?
Yes. Yes. Yes.
Okay. Okay.
You could introduce a delay. So, like, look at the first 5 lines and then output for the first line.
Okay.
And you would retrieve as much information as a 5x5 convolution filters, for example.
Okay. So,
and yeah, that could be interesting.
Okay. So, in fact, I have another question, because have you looked at what the people use on making printing line by line? Because they use concepts like error diffusion and so on.
Oh yeah.
This map is capable of, again, like diffusing error ahead. It's like when you finalize a decision, you can also diffuse an information ahead on the next lines.
Yes.
So I don't know if this concept has been used or not in terms of like pushing features or diffusing features ahead.
If it has been used, I don't know of anyone who has used that, but I think it's an interesting problem.
I have another question.
Sorry, I was not. Because you could correct some lines after the fact if you do that. So if you process some lines and you're not sure, oh, maybe this is a cloud, maybe not. Let's say it's not a cloud, and after that, oh, it is a cloud. Then, yeah, we could correct it. And actually, we see that this is interesting because for example, here in the output of ScannerNet, the CUNet in the first lines already knows that this is some clouds, some small clouds. But ScannerNet waits a bit before making the decision. We can see that here. And using a method like this with propagation, maybe we could fix these outputs.
Okay.
Yes.
on GNN, my question is, you mentioned that you are instantiating, like connecting pairs of vertices.
Yes.
But is it limited to the degree, or is the degree of the vertices limited at the end in the graph that you output?
No, it's not limited. In our method, what we do at the end is look at every possible pair of nodes at the end, and we output a score for each of these pairs. So we can have a link between any one of them. What we determined before is simply the stencil of the graph neural network. So in order to be more efficient in the message propagation, in the message passing.
But then you are not able to represent like a loop, just a single loop without any corner, right? Suppose there is a track, like a stadium track.
Oh, no, we don't do that.
We don't do that. Okay.
We would need to have multiple nodes. So if you have an oval stadium, you need to have 1 point for each small turn of the stadium.
Awesome.
Yeah.
Okay, well, I think I have more questions. I would also wanted to thank Gaétan very much, because during his thesis, he gave us participated to a course that I gave on deep learning. So I think I want to thank Gaétan very much for that, because the students really loved the course and all this fun Kaggle challenge that Gaétan organized. That was,
I think some of them are watching, actually. One of them is there.
Okay, now Florent Lafarge, thesis advisor.
Thank you.
Thank you. So you will be quick. I will not answer question.
Are you sure?
Yeah. But yeah, I wanted to thank you for the 3 years. I enjoyed working with you. Seeing you work on 3 different interesting problems. One was extracting some simple objects with a pixel-based representation. So simple without a strong geometric signature, like cloud or vegetation, something like that. The other one was extracting object more with freeform shapes.
Yes.
And the last one was more extracting object with structure object, I would say, that can be explained with a piecewise linear representation. So this last project, you were running a bit out of time, so you apply that only to roads, but the architecture has a potential to capture other type of structure object like buildings and things like that.
Yes.
You were running out of time, but definitely interesting to have the time to go for that.
Yes. I think so.
So it's quite complementary. Of course, you cannot solve all the remote sensing problem with this 3 solution, but at least for the extraction of object, you can cover a good range of objects.
Yes.
Yeah, so I just wanted to thank you, and also I wanted to say that beside the work from the PhD, you contributed a lot to the Titan team, I would say.
Thank you.
You were helping, participating to the research activity of other members by helping them. As Pierre mentioned, you were contributing to the teaching duty. You were also participating to some challenges and things like that.
Thank you.
It was very nice, and also you even bring a non-scientific contribution to the Yuliya. I was thinking to the
the coffee really important.
Now, thanks to you.
Yeah, I fought for that.
All the Yuliya employees. So,
yeah.
That's really a big change. And,
I hope you like
I
it.
think all the Yuliya employees are grateful for that. So that's all.
Thank
you.
Thank you. Thank you.
Thank you so much. So now
Thank you
the
very much.
way we will proceed is that we ask the attendees to just leave this room so that we can deliberate here. And then in about hopefully less than half an hour, let's say hopefully 20, because I know you have a time.
The question is, you are going to postpone a bit, or it might be a bit short.
Yes, maybe by 15 minutes. This is okay for Christian.
So
yeah.
I'm running.
I'm not.
Yeah.
Tell them
So
we'll be ready when we're ready.
15 minutes or
What?
so.
Yeah. It's more like,
Hopefully 20 minutes we can
be hurried.
conclude.
Okay, I will postpone after 15 minutes.
And then you can still wait.